Hi chaps, it's Mr. Pope from Wilmington Grammar School for Boys, and today we're going to be looking at circles. Just recapping some circle properties, some circle theorems, looking at some problems to do with coordinate geometry, just getting you a little bit more familiar with circles. Now, circular motion appears in lots of different things. For pure, you've probably seen it with complex numbers and rotating in the complex plane. Circular motion in mechanics is a really difficult topic. Vectors, you often solve geometric problems with circles and spheres quite a lot because they tend to be the loci of points of a fixed distance from a point. Circles, they're really important. They belong to a family of shapes called conic sections. And we'll actually cover them soon at some point. I forget which day I said I was going to look at conic sections. But yeah, circles. Okay, so let's start with some really basic ones. The area of a circle is just pi times the radius squared, and the circumference, which is the length going around the outside, is just 2 times pi times the radius, or just pi times the diameter d. I don't particularly care which one you use, just make sure you get it. So let's define some things. The radius is a point from the center of the circle to the edge of the circle. We'll call that r. Okay. So let's say there's a general point on that circle and it has coordinates x and y. We don't know what x and y are. Then if we think back to Pythagoras and I drop a line down like so, then this length is x and this height is y, because that's the whole point of a coordinate system. And we can actually use Pythagoras to show that x squared plus y squared equals some r squared. And actually, this is the equation of a circle centered at 0, 0 with radius r. Okay, now when we come to the second part of what we're talking about, we're actually going to go a little bit deeper than that. But for GCSE purposes, that's pretty much all you need to know in terms of circles. But we're going to be building on that today. So a recap really quickly of circle theorems. So to be honest, I forget the names of most of these things. I'm just going to tell you the basic properties. If I've got a circle and I've got the center, which is this red dot, then this angle here and this angle here are related in such a way that if this is theta, then this is 2 lots of the theta. And I forget the name of this. It's called various things. It might be twice the angle at the center. Some people call it that. It's a bit cryptic. Twice the angle at the center compared to the circumference. You might call it angles subtended by the same arc. Why is that? Because if I draw a line down from here and here, theta belongs to this arc and 2 theta also belongs to that arc there. And if it wasn't obvious already, the key kickers are these 2 points here and here. So if I was to draw a black line, say from here to that point, and then from that same red dot to that point, then this angle is also theta. And I can move it anywhere around between here and here, and it will work. Now what happens if I was to move it inside? So I was to take this point and say maybe go to here, and then go from here to here, then this angle, I'll call it beta, then it's actually this angle, which is 2 beta. It kind of flips over. And for similar reason, they both belong to the red major arc on the outside. Key points. What is an arc? An arc is a section of the circumference. If I draw a radius going from there to there, and from here to here, then this red section is called an arc. This orange section here is called a sector. If I draw a line from one edge of the circle to any other edge of the circle, like so, that doesn't go through the origin, then this is called a chord. And the area bounded by that chord, which is here, this is called a segment. Okay, cool, let's move on. So next up, a special case of what's going on here. Well, what have we got? We've actually got that this is 2 theta and this is theta, because you know they both share the same arc, which is this thing here. Okay, what does that tell us? Well, we know what 2 theta is. Theta is 180 degrees. So that means this angle here is always 90 degrees. So angles in a semicircle being 90 degrees. So angles in a semicircle are 90 degrees. There's various different things you could have called this. I'm paraphrasing here. But essentially, it's a special case of the one below. If I draw a line from there to there and similarly here to here, as long as they share these 2 endpoints with the diameter, then this angle here is also 90 degrees. And this one actually appears so much in mathematics. If you can show that there's a line between 2 points, and then I can construct a third point some distance away from that line such that, let's say this is P, let's say this is R, and this is Q, then P to Q is perpendicular to Q to R, then that automatically tells you that P, Q and R are on a circle. It's actually quite important. I'd probably say, you know, for GCSE, it's one of the dumbest, not dumbest, but just not used so much. But for vectors, I mean, it's used all the time. If you can spot that, you know, 3 points, the lines between them perpendicular, or rather from one point to another is perpendicular from that same point to another point, you can tell there's circles at play. Okay, so here, what we've got is this angle, let's call it A, is the same as this angle, we'll call it A, and this angle B is the same as this angle B as well. And this is angles belonging to the same segment theorem. The important point to note, the lines, the crossovers, don't have to go through the centre. They can completely ignore it. So for example, I could draw a different one where you've got some loopy ravioli shape looking like this, where this angle and this angle are the same, and this one are the same, and so on. Okay. Next up, this, when you have a 4-sided shape and all of the corners are on a circle, this is called a cyclic quadrilateral. And essentially, if this is A, then the opposite angle is 180 minus A, and if this is B, then its opposite angle is 180 degrees minus B. Okay, so opposite angles sum to 180 degrees. Okay, that's pretty clear. Next up, we have this one. So when a line just touches a circle, we've seen this before when I was talking about in calculus, this is called a tangent. Okay, a tangent touches it at one and only point, just there. So when a tangent meets a radius, it's 90 degrees. It's a right angle. A radius and a tangent are perpendicular to each other. Okay, now this one, there's a few different rules going on here. So what's going on is we've got 2 radii and 2 tangents. So the first thing to notice is there is a line from the centre of the circle to the intersection point of the 2 tangents. Okay. Next up, what does that tell us? Well, that tells us a lot of things actually, because we've actually split this angle in half and this angle in half. How do I know this? Well, I need to first prove or talk about this one first. Whenever there's a chord, okay, and a radius bisects the chord, like so, there is a 90-degree angle at play. So intersecting chords theorem is that if the radius is perpendicular to a chord, then it bisects it. Okay, and vice versa. If a radius bisects a chord, then it is perpendicular to it, and vice versa. If it's perpendicular to a chord, it bisects it. So if I look over here, what's going on here? Well, there is technically a chord from here to here, and I can draw a radius from there to the circle like so. So I know that this is 90, this is 90. And I can continue that line on. It's going to meet the tangents like so. The upshot of this is that this distance is the same as this distance. Okay? How can we prove this? Well, because, think about it, there's two triangles at play. There's this right-angled triangle up here, and there's this right-angled triangle down here. Now, how can we prove that they're the same? Well, they both have a radius in common. They both have a right angle in common, and they both share this hypotenuse in the middle in common. So by right angle, hypotenuse and a side, they are congruent. So that means this angle is the same as this one, these two angles are the same, and so on. So you've actually got a lot of things going on here. So when two tangents meet, they form a kite. If you've got the two radii and the two tangents meeting at a point, that's going to form a kite. Okay, what else have we got? Yes, alternate segment theorem. Alternate segment theorem. Segment, I'll spell that properly. S-E-G-M-E-N-T. Okay, what does this say? This says when a tangent meets a circle, and there's also the point of a triangle which meets that tangent as well, and that triangle is cyclic, it's all inside the circle, then, or rather the points map onto a circle, then this angle between the tangent and the triangle is the same as the opposite angle over here, and this angle to the left hand side is the same as this one up here. Okay, well, that's it. And then the final one, right, is the intersecting secants theorem. And what is a secant? A secant is a line. Well, it's a chord, but it's been extended. So if I draw a line from one point on the circle to another point, and then I continue it through, that's a secant. I could continue it back up here as well. Essentially, a secant is kind of like a long spike that goes all the way through a circle. Right, so what does this rule tell us? Well, this rule tells us that D times by C is the same as A times by B. So when you multiply the things together, it's going to work. So let's have an example. Let's say A is 2, let's say B is 6, and let's say C is 3. Then what must D be? Well, 2 times 6 is 12, so 3 times what is 12? D must be 4. That's essentially what that's saying. Okay, so it just means their products must be the same. Okay. So is there anything else? Oh, there's also an offshoot of that. So it's called the intersecting chords. Oh no. No. This is the bisecting chords theorem. bisecting. The intersecting chords theorem is a little bit different. So let's draw a circle. And let's draw two chords. So there's one and there's another. Don't necessarily go through the origin. So if I've got that colour, well actually let's preserve then they are essentially secants, and what's going on is if this is B and this is A and this is C and this is D, then in actual fact this rule applies to this as well. Okay, and that's called the intersecting, that is the intersecting chords theorem. Okay, now GCSE likes to play a really nasty game of saying, oh, well, you know, why is this? Prove it. Can you memorise the names of the theorems? And to be honest, no one cares past GCSE. No one literally cares. If you want the name of it, you just look it up. You just have to remember it's a thing. Unfortunately, you're going to have to memorise it for GCSE, but beyond GCSE, you don't. You can just say because of circle theorems. You could, you know, people are very lazy and they can just say angle BSQ equals angle MNP because circle theorems. They don't even actually write what the circle theorem was called or which one they used. They can just say, oh yeah, that's just one of the circle theorems we use, don't worry about it. As an example, they just don't care. They've got bigger fish on their plate, to be quite honest with you. And you know, if you've memorized all this stuff and you get how it works, then you're in for a whale of a time. If you want to practice this stuff, then go to Maths Genie, look at Maths GCSE revision, and look at all the, I believe it's grade 7 stuff. It's the circle theorems proofs. Knock yourself out. It's not, you know, it's okay, but I think this is like the fundamental, like basic-y stuff that you need to have down. And to be honest, some GCSE students can just get through GCSE and not know any of this stuff, and then they have real problems when they want to solve geometric stuff later on. But if you totally get this stuff and you've memorized it already, then pretty much ignore what I've just been banging on about. Okay, now circles in coordinate geometry. Let's get to some juicy stuff. Okay, so let's suppose I now have a circle that's not centered at the origin and it's doing something like this. Then, if it has a radius r and it has a center at AB, where x is A and y is B, so this is my xy graph, then the equation of this circle becomes, instead of x squared plus y squared equals r squared, it's now x minus a squared plus y minus b squared equals r squared. And now we're ready to play around with some coordinate geometry with some circles. Okay, so that's nice. So we would say that AB is the center and the radius equals r. Now let's suppose they give you the equation of a circle and it's not nice and neat like it is above. Let's say it's something like x squared plus y squared plus 6x plus 8x. Yeah, they just leave it as that, equals to 0. Okay, then where's the center and what's the radius? Well, that's quite easy. What we're going to do is you complete the square, but you're going to have to do it twice. What do I mean by that? Well, let's collect the x's. Oh, dear God, this is a y. There you go. I always do that. So x squared plus y squared plus 6x plus 8y equals to 0. Okay, so if we collect the x terms and we whack them over here, then we've got x squared plus 6x, and if we take the y squared terms and put them over here, then we're going to have plus y squared plus 8y equals to 0. Now I haven't actually changed the formula, I've just rearranged some bits. And now what you do is you complete the square on this thing. So x squared plus 6x, you halve the 6, that's plus 3. So it's x plus 3 all squared, and then you minus the 3 once you've squared it, which is a 9. Now you move on. Y squared plus 8y, well that's y plus half of 8, which is 4 squared, minus the 4 squared, which is 16. Now if you add the 9 and add to 16 to both sides, that's a plus, you get x plus 3 squared plus y plus 4 squared equals to 9 plus 16 on the other side is 25. So immediately I can tell the centre is, well, what plus 3, if this was equal to 0, what would x be? Well, that's minus 3. And if this equals to 0, what would y be? That's minus 4. And the radius is the square root of 25, which is 5. So you can quickly dissect the equation of a circle quite quickly, as long as you know how to complete the square. And again, that's one of the reasons why I emphasised completing the square in the previous last Monday's video. Not yesterday, the one before. Sorry, no, yeah, it was yesterday. Right, okay, so can we deal with the equations of circles? Yes. Okay, next up, just some little facts. If I have a tangent to a circle, right, so it's looking like that, I know that it's 90 degrees, and I know that if the gradient of the radius is perpendicular to the gradient of the tangent, then one of them, MR, that is the negative reciprocal of the other one. So for example, if the radius had a gradient of 2, that means the gradient of the tangent is the negative reciprocal of that, so it's minus 1/2. It's just little things to bear in mind. Other key points, say for example, and we kind of touched this in the pure last time, if I've got 2 points like so, let's say this is 2, 3 and this is 4, 5, and I want to find the distance between those 2 points, then I'd consider a right angled triangle, and then the 2 to 4 is 2 along and 3 to 5 is 2 up. So 2 squared plus 2 squared is 8, so this hypotenuse would be root 8, which is 2 root 2. So the length is 2 root 2. Next up, if I wanted to find the midpoint between 2 points, that's also quite easy as well, because you can imagine this gets split up into 2 smaller triangles. So instead of being between 2 to 4, which is 2 along, I only go 1 along, and instead of 3 to 5, that's 2 up, I just go 1 up. So 2, 3 becomes 3, 4. Another way of doing this is you take the x coordinates, so 2 and 4, add them and divide by 2. And then the y coordinates, 3 and 5, so you do 3 plus 5, then halve it. 2 plus 4 is 6, over 2 is the 3, so that's right. And 3 plus 5 is 8, over 2 is the 4, that's correct. So you can find the distance between 2 points, the midpoint of 2 points, perpendicular gradients, you know what a tangent is, you've got the equation of a circle, and you know how to complete the square twice on an expanded form of the circle to find out the centre and the radius. Okay, that looks like a 5, so I'm just going to tidy this up. That's a 5, that looks like an S. That's a 5. Okay, so let's put EG there. And to be honest, that's it, right? So hopefully it was a quick one today. I'm just going to leave some examples and go through it. Now, there's not a lot of theory with this stuff, but solving problems is going to be super duper hard. Now, I'll leave a question up. Just to let you know that this mod thing just means the distance. So the distance of A to B is 10 and the distance of B to C is 5. So I'm just going to grab a drink. You pause the video and have a go. Back uno momento. Just in case I use these videos later on in life, just to clarify, I'm recording these videos about a month into the coronavirus crisis of 2020. So I've been stuck indoors for the best part of 32 days now. I haven't been outside. Yeah, so me making these videos Hopefully it's interesting to you. It's keeping me busy at the very least, stopping me going stir crazy. And if you guys are learning something from it, that's fantastic. So, okay. A circle has equation this. Find the coordinates of the centre and determine the radius. Okay, so we've just got to complete the square twice. So x squared minus 8x. So that's going to be x minus 4 all squared, because half of minus 8 is minus 4. And then take away that squared is 16. And then y squared is 6y, half of 6 is 3, so it's going to be y plus 3 squared, and then minus 3 squared, which is minus 9 equals 0. I think it's going to be a similar thing here, isn't it? It's going to be x minus 4 squared plus y plus 3 squared equals 9 add 16 is 25. So the centre is x minus 4 equals to 0, so x must equal 4, and y plus 3 equals to 0, that means y is minus 3. And the radius of the circle is just the square root of 25, which is 5. Easy peasy lemon squeezy. Okay, for the next part, the points A, B and C lie on the circle such that AB is 10 and B to C is 5. Okay, right, let's think about this. I've got a circle. Here's my circle. Now, if I know the radius is 5 and A, B and C lie on the circle and A to B is 10, there's only one way this can happen. And that is if A and B are opposite ends on the circle and this is a diameter. Can you see why that has to happen? Because if you've got 5 there and 5 there, that's the only way you can get a distance of 10 inside of a radius 5 circle. Next up, you know B to C is 5. Okay, so let's say C is over here and B to C, there it is. That's of distance 5. Finally, if I draw a line from C to A, I know my circle theorems that this must be 90 degrees because angles in a semicircle are 90 degrees. And now this is actually really good because if I want to work out what AC is, I just work out this bit. And if you think very carefully, I've got a right angled triangle here. And if I spin it, I've actually got C is here. A is the long bit, that's B. 10 is the hypotenuse, and B to C, oops, it's not C, it's 5. Well, clearly, if I call A to C x, then x squared plus 5 squared equals 10 squared. X squared plus 5 squared is x squared plus 25. 10 squared is 100. So x squared is going to equal 100 minus 25, which is 75. So x equals plus or minus the root of 75, and that's 5 root 3, isn't it? Now, because we're dealing with an absolute length, we don't want the negative value, so x is just going to be 5 root 3. And x is AC, so we now have x is 5 root 3 as your final answer. Okay, was that it? K root 3, well, k in this case is 5, so k equals 5. Lovely, that's it. Okay, let's try a couple more. Okay, same deal, pause the video, give it a whirl, nice little problem solver, draw sketches, even if there's a sketch there. It's always good to draw your own sketch. Okay. Right. Okay, let's do this then. So, the line y equals 3x minus 4 is a tangent to the circle touching C at the point 2, 2, as shown in the figure 1. The point Q is at the centre of C. Right, find the equation of the straight line through P to Q. Okay, so what do we know? We know that the radius meets a tangent, they're at 90 degrees. I know this is a gradient of 3. So the gradient of the radius is the negative reciprocal of that, which is minus a third. So y equals minus a third x plus c. And I know it has the point, it's touching the point 2, 2. That point is on the radius. So the equation of the line P to Q is y equals 2 equals minus third of x, which is 2 at that point, plus c. So 2 equals minus 2 thirds plus c. If I add 2 thirds, that's going to be 8 thirds. So it looks like y equals minus a third of x plus c, which is 8 thirds. Now, some of you might know this already from GCSE stuff, but we're going to go over straight line graphs and all that stuff soon. Don't worry about it. The points, done all that. Given that Q lies on the line y equals 1, show the x-coordinate of Q is 5. Well, if it lies on the line y equals 1, then we know y equals 1. So we just set 1 equal to minus a third x plus 8/3. So if I times everything by 3, I get 3 equals minus x plus 8. If I minus 8 from both sides, I get minus 5 equals to minus x. So if I times by minus 1, x equals to 5. That's fairly straightforward. C, find an equation for C. Right. Okay, do we know what Q is now? Well, yes, Q is x is 5 and y is 1. So that immediately tells us that it's x minus 5 squared plus y minus 1 squared, and all I need to do now is find the radius and square it. But that's quite easy because it's just going to be the hypotenuse of this right angled triangle here. So let's think about it. If this point is 5, 1 and this point over here is 2, 2, then from 2 to 5 means you've gone 3 along, and from 2 to 1 you've gone 1 down. So 1 squared is 1 plus 3 squared is 9, 1 plus 9 is 10, so this is root 10. So the radius is root 10, so that means r squared is just going to be 10. So the equation of this circle is x minus 5 all squared plus y minus 1 all squared equals to 10. Okay, right, if you're getting the hang of this, well done. I'm going a bit quick, but you can always pause this and go back. Okay, for the last question, the figure above shows the equation 9x squared plus 3y minus 25 all squared equals 225. Whose centre is at C and its radius is R. Determine the coordinate C and the value of R. Right, so if I expand this, I will get 9x squared plus 3y minus 25 all squared is going to be 9y squared. Minus 25 times 3 is minus 75, double that, so it's minus 150y. 25 squared is 625, and this equals 225. If I subtract 225 from both sides, I'll get 9x squared plus 9y squared minus 150y plus 400 equals to 0. Now if I divide everything by 9, I'll get 9x squared plus y squared minus, and I believe this is 50 over 3y plus 400 over 9 equals to 0. If I complete the square on this, I will have x squared plus, this becomes y minus 50 over 3 halved, which is 25 over 3, squared minus the 25 over 3 squared, which is 625 over 9, plus 400 over 9 equals to 0, which means I'll have x squared plus y minus 25 over 3 squared, and then if I take both of these constant terms to the other side, I'll get 225 over 9, like so. In actual fact, what will happen here is you'll have a centre of x is 0, y is positive 25 over 3, and the radius is going to be the square root of 225, which is 15, over the square root of 9, which is 3, and 15 over 3 means the radius is 5. Okay, so the coordinates of C are 0 and 25 over 3, and the radius is 5. The points A and B lie on the circle, and the straight lines L1 and L2 are tangents. Show that L1 passes through the origin. Right, okay, so I know this point here is, what is it, 0, 25 over 3. I know this point A here is 4, 16 over 3. And I know the radius that goes from C to A is perpendicular because it's a tangent. So what is the gradient of that? Well, it's 25 over 3 minus 16 over 3. All divided by 0 minus 4, which is minus 4. And 25 over 3 minus 16 over 3 is 9 over 3, which is 3. So that gradient is minus 3/4. That means necessarily the gradient of the tangent is the negative reciprocal of minus 3/4, which is 4/3. So I'm dealing with a y equals 4/3 x plus a constant. But I know at that point when x is 4, y is 16 over 3. So when I substitute those points in, I'll get 16 over 3 equals 4/3 of 4, which is 16/3, plus a constant. Clearly the constant is 0, so that means the equation of that tangent line is y equals 4/3 x, and indeed that will go through the origin when x is 0 and y is 0. Yeah.